Welcome back to part 2 of my lecture on hypothesis testing for comparing two means. And let's get started right away with an example. And let's first state the null and the alternative hypothesis. So this flavor is going to both be similar and different to last lecture. It's similar in that we're still dealing with means of populations. So our null hypothesis and alternative hypothesis are really always going to be about statements about the mean, population mean, mu, okay? How it's different is that there's going to be two of them, okay? And I'll go over the null and alternative in a second. Let's just consider this example in which a nutritionist wants to know if a low-carb diet is more effective or if a high-protein diet is more effective, okay? More effective, and I'm sorry, it should be than a high-protein diet. Okay, so let's just edit that. Okay, so to test this claim, we need to be given a significance level, that's 5%, and a random sample of 50 is taken. Okay, 25 individuals are randomly assigned to each group. The results of each group are displayed in the table of the next slide. So first, we're able to state the null and the alternative just with the first sentence of this example. The null hypothesis that the two diets have the same mean. It's always a statement of equality, okay? So this is almost always the default null hypothesis. It doesn't have to be, it can be more complex, but for this class, it's almost always going to be the case that the mean of one group is equal to the mean of the other group. Here the group is low carb versus high protein, okay? And the alternative hypothesis is what the researcher wants to establish. So the researcher wants to know if the low carb diet is more effective, that on average people lose more weight than the high protein diet. Okay. Now, the alternative hypothesis comes in one of two flavors. One flavor being this one, that the mean of one group is bigger than the mean of the other group, and you just have to figure out which groups those are, okay? The other form of the alternative is that the mean of one group is not equal to the mean of the other group, and you can just calculate a confidence interval, okay? In that instance, if you want to test the hypothesis. So I'm focusing mainly on this alternative in which we have a greater than. So here's the data that is recorded. So for the low carb, the 25 individuals in that group lost an average of 5.5 pounds. They had a sample standard deviation of 5 pounds, okay? So quite a large deviation there, okay? And the question is that lost weight, of 5.5, is that due to randomness? Because there's quite a large standard deviation. Or is the high protein diet in which people only lost 4 pounds but had a smaller standard deviation, is that equally effective? Okay, so for our examples, we're always going to be considering the sample size in which we have 25 individuals, okay, equal, not to always 25 that number, but that each group has the same sample size. That's what we're going to consider. Now we want to test this hypothesis at the 5% level of significance. So here's what we need to use, okay? We need to use a t-statistic because we're using sample standard deviations. Our t-statistic we've seen has 2n minus 2 degrees of freedom, which in this case is going to be 2 times 25 minus 2, or 48 degrees of freedom. Our t-statistic is always going to be our observed value minus our hypothesized value divided by our standard error, okay? Now our observed value is the difference in means. We see that's 1.5. Our hypothesis value under the null Well, our null hypothesis that they have equal means, so the difference should be 0. Okay, and our standard error we've seen in this textbook is calculated in the following way. I square the standard deviation of 1, add it to the square of the standard deviation of the other group, and I divide by the sample size. Careful here, the sample size is the number of individuals in each group, not the total sample size of the study, which is 50. So I divide it by 25 because there's 25 individuals in each group. I come up with my standard error of 5.83. Okay. So now we want to go ahead and calculate the p-value. And if I calculate my p-value, well, we go ahead and calculate our t-statistic. Okay. And I want to point out the reason I'm calculating the t-statistic is greater than, that comes from our alternative hypothesis. If we see a value of the statistic that is greater than 0 or positive, that indicates that people in the low carb diet did better than those in the high protein diet. Okay. So they did 1.5 pounds better on average. The hypothesized value is 0, and we divide by our standard error. We calculate the probability t-distribution with 48 degrees of freedom is bigger than 0.25. And from your calculator in the book, you'll get 0.8 for a two-tailed value. But since we have a one-tail greater than probability, we divide by 2. Okay. Now we could also do a critical value method and compare the t-statistic of 0.25 with a critical value of 1.677 and fail to reject it again, reaching the same conclusion. Now how we got that 1.677 is also from your t-distribution calculator, one of them coming from the regular t-distribution calculator and one of them coming from the inverse t-distribution calculator. Okay, now let's consider another example. Since we finished this last one, in both instances we failed to reject it. Okay, our t-statistic here was less than 1.67, so we failed to reject it because this is a greater than value. Okay, it was not large enough. And if we use the p-value, we get 40%, which is not less than our cutoff of 5%. Okay, so here's another example in which a sociologist believes that male and females have different wages. Okay, so to test this hypothesis, a random sample of 25 males and females taken, and they find that the average hourly wage for females is $16.25 with a standard deviation of 3 per hour, and for men is $21.75 per hour with a sample standard deviation of 4 per hour. So our researcher wants to test this hypothesis at the 1% level of significance. And to clarify, the test of hypothesis is that the average salary of males is equal to that of females. So it's saying that the difference in wages, the observed difference, is due to random chance in our selection. Okay, that versus the alternative that the average wage of males is greater than the average wage of females. Okay, so let's test this hypothesis at the 1% level of significance. So we have the following information. Okay, and we calculate our observed value. That's just the difference in sample means. So that's $5.5 an hour. And the hypothesized value or difference, if they had equal wages, would be 0. Okay, so we're going to subtract 0. And then we calculate our standard error. And we see the standard error is $1 per hour. Okay, so if we go ahead and calculate this, we'll calculate the p-value. We're going to calculate the probability t-distribution with 58 degrees of freedom is greater than the observed value minus the hypothesis value divided by your standard error, well, that's the probability t-distribution with 58 degrees of freedom is bigger than 5.5. And when you plug that into your calculator, you get 0. And that's less than the cutoff value of 1%. So we reject our null hypothesis. Now, I'd just like to point out here this greater than. It came from the fact that our alternative was that the mean wage of males was greater than that of females. And if we see a value of this that's positive, that indicates that the mean wage of men is greater than that of females. Okay. Now, this 0% indicates that the difference in wages is not due to random selection. We would not expect to see that big of a difference in wage due to random selection. Okay. And it must be attributed to something else. Now, what it's attributed to, well, it could be gender discrimination. It could be that you don't have a random sample in your population, that for some reason maybe you selected a very high or wealthy. It could be that the men for some reason have a profession that's different from females, that you're not sampling the same profession of population of men versus women. Maybe you're comparing engineers to a lower paying wage of women. So what that difference is, so there is a difference. That's what our p-value tells us. But why there's a difference, it doesn't answer that question. Okay. Now, if you have accounted for all the variables and you got a p-value of this, and you didn't believe that there were any other variables that affected age, then yes, you should say that this difference is due to gender discrimination. There'd be no other option. Okay. Let's move on to a case study in R, in which this is real data that has the starting salaries from different job categories at a bank that was sued for sex discrimination. And we have the data on 32 male and 61 females and employees. And what we're going to compare is always the starting salary. Okay. So I'm going to have this B cell, which is the annual salary at the time of hire, and that's what I'm going to look at. That's the starting salary. This salary 77, I'm going to ignore that. Okay. Then I have the gender or sex of the employee. I have the seniority in months since first hired of the employee, the age of the employee, the education, and the experience. For now, all we're going to do is we're going to compare starting salaries of men versus women. And when we get to regression or even ANOVA, we can try and include some of these other variables as possible discrepancies of wage. But first, let's just compare starting salaries of men versus women. This is the data. So base salary is given here. You have the sex, you have the seniority, the age, the education, and the experience. The seniority is measured in months, so is the age, so keep that in mind. One thing to keep in mind is, this 50-40, for instance, doesn't resemble a realistic starting salary today, but this is real data, and you have to consider that this was data taken from the 1960s and 70s, okay? So here's our question. Do males earn more than females at this bank? And test this hypothesis at the 1% level of significance. So the null hypothesis is that men earn the mean wage of males equal to the mean wage of females. The alternative is that men earn more than women. So we're going to test this, okay? And when I test this, the command in R is just t.test. I apologize there. Is just this command right here, and it's going to test starting salaries according to the two groups of sex, males versus females. What we'll see is this T statistic will have this degrees of freedom, but what I'm really interested in is this, that p-value. Okay. Now, I like to point out our degrees of freedom is fractional because we have an imbalance. The sample size for men is not the same as the sample size for women, so that in R, it knows how to compute this for you, and it uses a slightly different formula to calculate it. Okay, and I'm not requiring you to know what that formula is, but I am expecting you to be able to use some software to calculate to do this statistical test and calculate its p-value. So the p-value is 3 times 10 to the minus 7th. And the alternative hypothesis is that the difference in means is not equal to 0. So this is quite strong evidence with this p-value that men do not make the same wage as women, because the p-value is much, much less than 1%. Okay. And if I had to calculate a 95% confidence interval, it'd be from basically minus 1100, I rounded to minus 536. I have the average wage of women, which would be 5,138, compared to that of men, which is 5,956. Now let's just look at this. The p-value is very small, so it's very clear evidence that the means are not equal. And it's estimated that the difference in wage is the difference in salary on average. So men on average make $818 more. And because there's variability in our data, we can consider a confidence interval, which would say that the mean difference in wage could be anywhere from $536 to $1,100 more in starting salary. Okay, so that's just a little case study, and this is actually related. This is exactly the data that you're going to be using for your gender discrimination project if you chose that project. Okay, so that's all that I want to say on comparing two means. And thank you for listening and watching to this lecture. I hope you're having a good one.